Welcome to our video here on Taylor polynomials, day one. Actually, we're talking about Taylor and Maclaurin polynomials here. So essentially what's happening with Taylor polynomials and Maclaurin polynomials is we take functions that are weird by like trig functions, exponential functions, stuff like that, and we want to rewrite it so it becomes a polynomial, because with some of those weirder functions that involve trig or anything like that in it, it's hard to take the derivative or the integral of it. But we can always take the derivative integral of a polynomial pretty easily. So the whole idea here is to take some weird function and rewrite it as a polynomial. So the only problem is the polynomial isn't exact as we get through it. So let's just say that we have a graph right over here, and this is sine x. So I'll kind of trace sine x right here. So this is sine x in pink. Okay. Now, in my Taylor polynomial, I have all these different terms, and I'll explain what each term means. But essentially, if I just use one term, then I would get this line right here, which does not match up very well. But if I do two terms, let's do three terms. Looks like the other one they have here. It looks like this. So it kind of matches. All right. It matches like in here. If I do five terms, it matches up a little bit better, and it matches up kind of in this range right here. And if I do seven terms, it's going to match up even more accurately, even more further away. So the more and more terms we use for a Taylor polynomial, the more and more accurate it's going to be. So here's our formula. So all it is going to be the constant plus the derivative of the constant. C is whatever we're being centered at. So for sine of x, we were being centered at 0. And then we do the second derivative over 2 factorial, and it kind of repeats itself with that. So it's the whatever derivative of that centered value over n factorial. So if we want the seventh term, we would do the seventh derivative over 7 factorial, and all that fun stuff. Okay, so first, before we talk about Taylor polynomials, we're going to talk about Maclaurin polynomials, and that's when we're centered at 0, and these are really the Mickey Mouse examples. Okay, so this is the formula that matches that. Okay. So let's just go ahead and do our first problem here, which is finding the find the Maclaurin polynomial of degree n equals 5 for sine. So what I need to do here is I need to find what the first derivative, second derivative is, third derivative, all that fun stuff. So I need to find out what f of 0 is first off. And what's f of 0? You just plug that in, you're going to get a 0. Okay, I need the first derivative. So the first derivative of x is going to be, derivative of sine is going to be cosine. And then so f prime of 0 is going to be 1. Second derivative of x is going to be negative sine x. And if you plug in a 0, you're going to get a 0. Third derivative of x is going to be negative cosine x. So if I plug in a 0, I'm going to get negative 1. I'm going to keep going all the way out to the fifth one here. So the fourth derivative, going Roman numerals now, is going to be sine of x. So we can kind of start repeating ourselves. And this is going to give me 0. And then the fifth one, again, that's a Roman numeral. It's going to be cosine. If we plug in a 0, we're going to end up with a 1. Okay, so this is kind of all helping me figure out what these coefficients are. So let's just go ahead and plug everything in. So a polynomial of fifth degree, that's what that means, p sub 5. A polynomial of fifth degree of x is going to be f of 0, which is 0, plus first derivative of 0 times x, so 1x. Plus second derivative, which is 0 over 2 factorial times x squared, plus third derivative is going to be negative 1 over 3 factorial x to the third, okay, plus 0 over 4 factorial times x to the fourth, I know I'm squeezing on here, plus, and then 1 over 5 factorial x to the fifth. And there you go. That's a non-simplified version. Now, obviously, we can rewrite this, taking out all those zeros and simplifying some of the stuff. So I'm going to get x minus X to the third over 3 factorial would be 3 times 2 times 1, which is 6. So minus 1/6 x to the third. And then 0 and then plus, that'd be 1 over 120 x to the fifth. Okay? So if we were to go ahead and, I don't need to sketch it because it is right here. I would get this blue right here. If I were to go ahead and graph it, I would get this blue guy right here, which, again, if you see, it matches sine really well towards the center, not so much as you get further and further and further away. All right, so find p sub 5 of 1.2. So all we're going to do is just plug in at 1.2 into this polynomial. So we're going to do, this is going to equal 1.2 minus 1/6 of 1.2 cubed plus 1/120th. 1.2 to the fifth. Okay, you don't need to see me do that in the calculator, so we'll just pretend. And I got an answer of 0.932039. Okay, I just want to write out a bunch of decimals because I want to kind of show you what the error is here. So what's the actual value of f of 1.2? So if I actually type in sine of 1.2, my actual value would be, well, you know what? I have the wrong thing here. This should be, ignore my answer right here. It's close. I was looking at the wrong thing. Maybe I really should have used a real calculator. This is 0.932736. This actual value is 0.932039. Okay. So again, like super duper close. So what's the error in the approximation? So if I just subtract these two values from each other, the error here is going to be 0.000, because if you look, they match the first three decimals. 697. All right, so that's the error for that. Now let's go ahead on this side, and let's go ahead and plug in a 2.1. So if I were to plug a 2.1 into my original polynomial here, I would get 0.8. I'm looking at the correct one now, so you can trust me. 8968417 All right, if I were to actually find sine of 2.1, and again, this is further away from the center, so it's not going to be quite as accurate. It's going to be 0.863200936. Okay, so this is my estimated polynomial of sine. This is my actual value of sine, and the error still is pretty small. It's 0.033632. So the difference there. So how does the error compare? It's much smaller error for x equals 1.2. Okay. And why is that? Well, because as we get closer and closer to the center of the polynomial, the more and more accurate we get for these series. So that's really all Taylor polynomials are. It's just taking something that, this one wasn't too weird, just trig, taking this and rewriting it as a polynomial out to whatever degree they want. Okay. So now let's do f of x equals ln of x. So this is another one that's kind of weird. We're going to do one out to degree 6. Okay. So let's find all these derivatives. And this is going to be at c equals 1. So now I'm actually using this formula right up here. So I'll go ahead and pull that back in when it's time to rewrite that. But we're going to go ahead and find f of 1. So I want to go out to 6. So I need to do f of 1. If I plug in a 1, which would give me 0. F prime of x is 1 over x. F prime of 1 would be 1. F double prime of x is going to be negative 1 over x squared. Just trust me on that one. And you can actually do it yourself. That's going to give me negative 1. Triple prime of x, that's going to give me 2 over x to the third. So if I plug a 1 in, that's going to give me a 2. Fourth derivative is going to be negative 6 x to the fourth. So that's going to give me negative 6. Fifth derivative of this is going to give me, it'll be a positive 120, no, it's 24 over x to the fifth. This is 24. And oops, wrong Roman numeral. If I take the sixth derivative, it's vi. This one will be negative 120 over x to the 6. So this is going to give me a negative 120. So those are all of my coefficients. So now I'm going to write this out using this formula right up here. So this is going to be f of 1, which is going to be 0. Okay, so P6 is going to be, and I don't need to write out to 0, okay? So this is going to be 0 right there. And then f prime of 1, which is 1 times x minus c, and c is 1, plus the second derivative, which is negative 1. So negative 1 over 2 factorial x minus 1 squared plus, and kind of get the idea. Okay, so we're going to do the next one. So the third one is going to be 2 over 3 factorial x minus 1 to the third plus, we get negative 6 over 4 factorial x minus 1 to the fourth plus, this should be 24, not 25. 24 over 5 factorial x minus 1 to the fifth plus negative 120 over 6 factorial, which is going to be x minus 1 to the 6th. All right, and that's the entire polynomial. That's going to match ln of x. It's going to be really, really accurate, close to 1. But the further away from 1 we get, less and less and less accurate it's going to be. Okay, I could write this one out a little bit neater, and I'll do that right down here. If I simplified this one, this is the same thing as x minus 1 minus 1/2 x minus 1 squared, 3 plus 1/3. It should be 1/3, right? I'm just double checking my work. Okay, 1/3 x minus 1 to the third minus, it should be just 1/4, right? Yes, 1/4 x minus 1 to the fourth. It's there. This is the fourth. Plus 1/5 x minus 1 to the fifth minus 1/6 x minus 1 to the 6th. Okay, so it's the same polynomial right there. I'm just simplifying it for you because if this was multiple choice, this would be the correct answer. All right, so again, if I plug in a 1.8 into my estimation here, I'm going to get 0.570112. If I plug in 1.8 into my actual value, so ln 1.8, that's going to equal 0.5877866. So what's the error? Error is going to be 0.01764. Sorry, 0.174. And that's my error. Okay? So not so bad. So we're going to be wrapping this one up with this question right here. Suppose that g is a function that's continuous derivatives. So this is really nice because it gives us all the derivatives. Write out the degree 3 polynomial. So all this work I did up here, it's already done for me. So this is one of those questions that's super duper nice. So the polynomial of 3, a power 3 is going to be all centered at 2. So if you want to kind of keep this up here for you, for your reference, okay, is going to be f of 2, in this case g of 2, which is going to be 3, okay? G prime is going to be minus, so it's going to be minus 4x minus 2. It's centered at 2. Second derivative is going to be plus 7 over 2 factorial x minus 2 squared. And then this is going to be minus 5, because it's right here, over 3 factorial x minus 2 cubed. All right, and then you can simplify this if you want. Not really that big of a deal, so I'll just kind of leave it like this. Okay, and that's going to wrap our video here for our first day of Taylor Polynomials.